Welcome to a tutorial on electric force. This should help you out on the activity that we have planned for this week, the tutorial that you'll actually do at home. What this little application allows me to do is to drag charges around and check their effect on the test charge, which is my little black charge there. You can kind of see it's actually kind of a game, like a little hockey game that gets more and more difficult, but in this case all we're using it for is for the ability to take a look at electric force arrows. Now in this case right here, you can kind of see as I move this charge in here, I have some sort of an effect, and I can kind of take a look at it. If I place it in this location and go half the distance, I can see what happens to the force, half the distance again, and you can kind of see this effect that as you have the distance, you much more than double the force. In this case, that makes sense based on our relationship for electric force. In this case right here, the force electric. We'll have to label these. I'll go ahead and call this, we'll call this B because it's black, and we'll call this one red. For this charge right here, you can see the force on the black by the red is going to be equal to K, our constant, Coulomb's constant, times the charge of the red times the charge of the black divided by the distance between the red and the black squared. There we go. Although subscripts make a difference because, as you'll see, it can get complicated when we have multiple charges. But here this is showing you that in this case right here with this r squared term right there, as you have the distance, it's an inverse square, so you'll increase the force by a factor of 4. And that gets us our ability to essentially calculate the magnitude of this force. The direction, of course, is indicated by the fact that these two are like charges. Now, things get more complicated. But for right now, I just want you to focus on this charge right here, this electric force on the black by the red. And what I'm going to do here is I'm going to go ahead and bring in another force. So notice in this case I'm going to bring in another positively charged force, and you can kind of see the effect on the black charge. Now I have two forces. But as I move this around, notice that the position, the magnitude of the force on the black arrow by this new charge has absolutely no effect whatsoever on the first force arrow. In other words, I can even move this in between here, kind of blocking. I can't do anything. I can put it over here on this side, something like this. No matter what I do, it has no effect on the first force arrow that we drew. And that's an important thing to understand with electric forces is that the forces are calculated completely independent of any other charges that you have in the vicinity. So in this case right here, if we wanted to add the total effect of these two charges, I'll kind of put the charges like this, you can kind of see that I have my original force arrow. In other words, I have this original thing, which was our we'll call it the force on the black by the red 1. That was our first charge that we had there, was equal to that K, Q, Q over R squared. And then we have this additional force in here. You can kind of see what we're going to have to do now is recalculate this number, a force on the black by red 2. Something like this, and now we're going to get a K, Q, Q over R squared, but all for the two terms. Okay, and then we can add those two forces. So in this case right here, you'll notice the important point to notice is that when you have two forces, you're going to have to calculate this twice. Now, why am I emphasizing that? That seems kind of obvious. It seems like we should be able to do this. Well, it is a common mistake for students to do something like this. They will write, because I have these force 1 and force 2, they will write an equation that says the force, the total force, right, electric force, is equal K Q1 Q2 over R2 squared. In other words, they'll use these two charges and the distance between here, that radius right there, to get the total force. And you can never do that. That only gives you a single force. In this case, it would give you the force between those two charged particles. But what we're interested in this case is the net force on this one. When you do net force and you have more than one electric force, you will always be calculating multiple terms and adding them together. Now in this case, of course, I've given you an example where the two forces are in line and we can just add them, make our calculations and add them numerically. But I could just as well have put the two charges in some sort of an arrangement like this. And it quickly becomes clear that the total force on the black charge is equal to the charge on each of the other ones, but we can't add them arithmetically. We're going to have to add them as vectors. And the way that works, of course, is something like this. What we're going to have here is the force. We'll again call this 1 and 2. You'll have a force on the black by 1 in this direction, and then you'll have a force on the black by 2 in this direction. And then, of course, what we're going to have to do is we're going to have to go back to what we have used in the past and do vector addition. So you can kind of see here that this first force has maybe a component in this direction and a component in this direction. The second force has a component in this direction and a component in this direction. And the net force is going to be the vector sum of those two, which is going to be a vector that kind of points off in this direction, our F net. We have done this before, of course, when we were dealing with tension and other things, but keep in mind that with electric force, nothing has to be touching the two particles, and we can have kind of more complicated arrangements than we had before. So we're going to be back into vector addition of forces to be able to calculate and conceptualize what's happening here with multiple charges. Okay, so let's go back to the original setup. And you can kind of see here, if I were to keep adding additional charges here on this side, I'd have some kind of a more complicated, but you could probably see some sort of a vector sum on my black charge by the total of the other charges. Now, important thing to keep in mind here is because of this importance of the distance between the two charges, the distance between a charge and our test charge there, you can see that all of these force arrows are not equal in magnitude, and they are not always equal in length. That has an effect on our net force on a charge. In this case, I've added 1, 2, 3, 4, 5, 6 of these positive charges, but notice the total force, or the net force, on the black particle is not 6 times the initial force. And the reason is, of course, because of all of these angles and the increasing distance away from each of these charges. In other words, I would have had my original force from the first particle, but the other additions are both further away and off at some angle. And so my net force would be these components here. It would be maybe like a component of this one in this direction, and a component in this direction, and the component in this direction, and I would have to add up all of these individual components to figure out the total force. Okay, now quickly to look at a different viewpoint from this, we're dealing with forces, and you'll be dealing forces in your lab sheet, but notice that in this case I can toggle on the field. This is going to get complicated when they put this on, but there's my total field. And in this case right here, you'll notice, if I focus in, again, what I'd like to do is I'd like to focus in on just my test charge right here. If you focus in on the test charge, you'll notice that all of the forces that are acting on it kind of combined to show you that there is a field that is pointing in this direction. And you can kind of see that with those black arrows. In this case, I'm switching between a force viewpoint and a field viewpoint, but notice that the net force on my test charge will be in the direction that the field is pointing at that location in space. And all of this kind of conforms and confirms what we're talking about, the possibility of doing vector addition for electric force problems. Okay? All right, so last thing I'd like to show you here is just some other arrangements. I'm going to get rid of this field because it gets a little bit complicated, but some other possible arrangements. Let's go ahead and clear this out and say that sometimes with the problems that we'll have arrangements that are symmetrical in some way. So one that you'll see on some AP problems are equilateral triangle. And of course an equilateral triangle has angles of 60. And so you can kind of see here that I can do some sort of a vector addition to figure out the net force on my test charge. And it'll involve a little bit of trig. But in this case right here, with this arrangement, we know that since the angle on this side is 60 degrees, we would know that these angles are 30 degrees, and rather than just adding components, we could actually calculate now using trig the different components of these forces and figure out the magnitudes of each of the components and find out how to calculate the total net force on a product, on an object. Okay, so that would be one possible arrangement. You can also get arrangements sometimes that look like this. They'll have a test charge at the corner of a square, let's say, something like this, and they ask you what the net force is on the particle, something like that. And you can kind of see how you could use angles and distances to figure out the magnitude of a net force by doing some sort of a vector addition. And the last arrangement I'd like to show you is one that we'll use and develop more in class, but it looks a little something like that first example that we had, where you had a series of charges, something like this, and this would approximate the sort of net force that you would get on a particle if it was next to a charged plate. The idea here would be something like this, that this right here is actually a charged metal plate. And notice that when you take the vector sum, or if you look at the field, in this case right here, oops, I guess I can't turn the field on with that highlighting on. Let's go back to our main screen. There's our field. You can kind of see that each little contribution from the charges along the straight line create a field that goes away from the plate. And in this case, a net force on a positively charged particle would be, in this case, to the right. I could actually add also, in this case, see if I can get back to my original screen here. There we go. What I can do is go ahead and add negatively charged particles over on this side, and I get a condition where I have two charged plates, one positive, one negative, and you can kind of see my little test charge in the center there. And this is a sort of, again, another arrangement that we're going to see. And notice that it creates this kind of a evenly pointing field in between the two charged plates. This is all a factor of you can either think of it as adding up force vectors. In other words, if we take a close look at our test charge, you can kind of see how all of those force vectors are going to be pointing to the right if they're added together as vectors. And you can also do it as looking at these individual field lines, showing that you have this kind of a uniform field pointing to the right. That's another arrangement that we will use going forward. Hopefully this summary will help you with the lab activity, the tutorial that you will do on your own, and it'll give you some problems to help you with the quantitative aspect of electric force. Thanks for joining me.